In this video, I'm going to be talking about the resolution of an image through a single slit. It is part of 9.4 of the IB HL Physics syllabus, so this really is not relevant to SL students. First, let's start by taking a look at the success criteria. Please pause and read through what I plan to cover in this video. So before I can get started on this, we really need to know about the interference pattern caused by a single slit. If you're aware of this, great. If not, I suggest you go and watch my video on single slit interference. When a monochromatic light goes through a single slit, we actually get an intensity pattern looking like this. We have light waves coming through the opening, and they're going to have to travel different distances, and we get this pattern. So let's think about what this really means. This high intensity here means it's going to look like a bright spot, and low intensity here will look like a dark fringe. So notice we have a central maxima that is twice as wide as all of these secondary maxima. The other thing to note is that we go from a very intense bright down to this. I usually tell students to do this less than 20%, and so forth. It keeps continuing down. Okay. Now we have in our data booklet the equation for this. Lambda being our wavelength, b being the width of the slit, and in this case theta is going to give us the angle to the first minimum. That's really important. Okay, so if I have my slits down here and light comes through, the angle we get from the center to here would be theta. We can have it in both directions, and it will be the multiple would give us the different orders: first, second, third. Now all of that was from 9.2, and we had a single source with a single wavelength. But what we're going to cover now is what happens if you have two sources of light and not one. Notice we will have the same wavelength. We won't have examples that have two different wavelengths for this. An example I like to use is a car driving towards you at night. When the car is very far in the distance, you see a single headlight, and it's only once they get closer and you can actually resolve them that you can see that there are two headlights and not one. So in my diagram here, I've got two objects, and this dotted line represents the center or the straight line through the opening to where I'd get my single slit intensity. And you can see I've got my central maxima, and this would be my first minima, and it would continue on like this. Now my second object, it has a different line that would go through the center to where it would make its central maxima, and we can see that they are separated there. Another example of this would be looking well into the distance and say, are there two birds on the wire or are there one bird on the wire? I think you can get the point. At some point, we actually can't tell the difference between one or two. Now, in both of these cases, can you think of what's acting as my single slit? It's my eye. It would be the, well, more specifically, the pupil. It would be a circular opening just like this. We call it an aperture, and we'll discuss more about these types of openings in our next slide. Okay, so in this first picture is what we had on our previous slide. We had two separate sources, and we could actually see after the single slit two different intensity patterns on our screen. And in this case, there was no problem with us distinguishing between them, so we're going to call these well resolved. Now what's going to happen though is as they come closer and closer together, the angle between them is going to get smaller, and these intensity patterns are going to come closer together. Now in this case, you can see that I've got two lights still. In fact, you can see that they're kind of pinched together right here. In this case, we're going to say that these two are just resolved. And if you take a look, there's a very specific thing that's happening right now. If you see this outline here, notice where it is compared to the one that has the blue outline. The reason this becomes really important is you can see in the next picture, even though they were two sources, they are going to look like one single dot. In other words, they might look like a very fat dot or a very elongated source, but I can no longer tell the difference between having one light source and two. In this case, we're going to say they are not resolved. So let's look at that special case in the middle. We had it that we were just resolved, and this comes up to Rayleigh's criterion. He was the one who said two light sources will be just resolved when the center of one diffraction pattern must directly overlap with the first minimum of the other diffraction pattern. So let's take a look at what this looks like on our diagram here. So I have this one here outlined in brown, and if you see, its central maximum occurs over top of the one that's outlined in blue. If I look on the other side, because there's a symmetry, we have the central maximum of the blue over top of the central maximum of the brown. So let's see that again. He says the center of one diffraction pattern must directly overlap with the first minimum of the other pattern. Remember where this occurred. This was theta equals lambda over b. He's saying that the last time we can actually see that there are two separate light sources is when this occurs. Now, before I go any further, there's actually a difference I need to point out. We have this equation here in 9.2 and this equation here in 9.4. And you might say, well, what's the difference? Does it really matter? Well, yes, it does, because this one is only true for circular apertures. If I were you, I'd be writing that in my data booklet. No, you don't get your written data booklet in the actual exam, but when I'm studying, I like to see that these things stand out. This previous one that we had is for a slit. So in other words, we've got horizontal sides. Now you might say, well, why is the 1.22, where did it come from? Well, we're not going to go into the math because of it, but let me just point out that when I have a circular aperture, rather than having a whole slit, I need a bigger angle in order to be able to resolve the two sources. Okay, so let's use this with an example. So I've got here, draw two lines on a white sheet of paper, 2 millimeters apart. How far away can you be and still distinguish the two lines? Go ahead and try it out. I did this with blue ink, so that means my wavelength is going to be, let's say 450 nanometers. That's approximately blue light. And when I put it on the wall and walked away in the hallway, I got to around 8 meters. So let's start to set up our diagram. So I used blue ink. Here we go, 2 dots, about 2 meters apart. I'm going to have our two sources of light go through our opening B, and that will be our pupil in this case. And let's say that's our retina. Okay, so here's our two rays of light to the central maximum. And what else do I know? Right, there's my theta. And I also then have the distance between my pupil and where the two dots were is 8 meters. In order for them to be just resolved, we are going to have the maximum of this one here, let's say, and its first minimum will be here, which is why we can use our single slit interference equation. And it's going to be 1.22 because we have our pupil, which is a circular opening. Now at this point, I do know my lambda, and I'm looking for B, so I need to find theta. Now, in order for me to do this, I'm going to actually go and use this triangle right here. We're also going to be using our small angle approximation. So let me just draw that triangle a little bigger. We've got over here 2 millimeters. Here's my theta, and this was my 8 meters. Now, we're going to make an approximation and say it's basically a right angle. And at these small degrees, or in this case radians of theta, we can actually make our small angle approximation. If you remember, tan theta is going to be approximately the same as sine theta, which is approximately the same as theta, as long as we're working in radians. So let's check this out. Let's say it's sine theta for what we have here. That means theta, or sine theta, would be opposite 2 times 10 to the minus 3 over top of 8. And now I'm going to pick up my calculator, and it's going to give me my value of 2.5 times 10 to the minus 4 radians. Now if I go back and I put that into our single slit interference pattern equation, we have 2.5 times 10 to the minus 4 equals 1.22 times lambda, which was 450 times 10 to the minus 9, all over b. Again, picking up my calculator and putting that in, and I get 2.2 times 10 to the power minus 3. And if you look online, that's probably a small value for a pupil. Maybe it was bright out. Remember, I only did one significant figure when I measured my 8 meters. So here's another example, again using an eye, but instead of saying, hey, I want to have them resolved, it's the opposite. So when we use the laser printer, we want our dots to be so close together that we don't actually understand that they are made of separate ones. It's kind of interesting to look at these under a microscope where you have better resolution. So it tells us to take the pupil of the eye to be 3 millimeters and the distance from the paper to the eye to be 35 centimeters. Find the minimum separation of two dots so that they cannot be resolved. So let me do a quick little diagram. Okay, so here's my diagram. We don't know the distance between these two dots that we're looking for. We do know that it's 35 centimeters away from your face, and we're going to use an opening of your pupil of 3 millimeters. So let's find the minimum separation those two dots are going to be so that they cannot be resolved. Now we're going to need a wavelength of light, and we know that visible light is between 450 and 700 nanometers. So for the purpose of this, let's go and take lambda equaling 550, kind of in the middle. Don't panic. If you were doing the IB exam, they would actually have to give this to you. So let's first figure out what we can using our equation. So we have a circular aperture, so we're going to use the one that has 1.22 times theta over b, and I'll put my numbers in here with our lambda being 550 nanometers, writing them in meters because we need the units to cancel out, and the opening of our eye, and I have 2.24 times 10 to the minus 4 radians. And again, I'm going to use my small angle approximation that tan theta is approximately the same as sine theta, which is approximately the same as theta. And we can do this. If you haven't done it before, check it out. At this small value, tan theta, sine theta, well, let me just actually do it for you. So making sure your calculator is in radians, if you put just 2.24 times 10 to the minus 4 in your calculator for sine, you actually will get 2.239999, so basically 2.24. And if you put it in for tan, you get 2.24000, which is basically 2.24. So, sorry, times 10 to the minus 4, of course. So in these cases, you might say, but it's not exact. Well, with our 3 significant figures, it is rounding to the exact same number. So let me get rid of this. Now, back to our question. From this triangle again, right here, I see it best as sine. I see opposite, which is my x, over my hypotenuse, which is 35 centimeters. and that's going to equal my radians, which would be 2.24 times 10 to the minus 4. Rearranging and picking up my calculator, I'm going to get 7.84 times 10 to the minus 5 meters, which would be the same as 0.0784 millimeters. Okay, so we're going to get them very close together. So let's go back and look at the success criteria one more time. In this video, I looked at the single slit intensity from 2 different sources and how they interacted after going through the slit. Would they be well resolved, just resolved, or not resolved? And finally, I used examples with this resolution with our eye as the slit, but you could also expand this to using telescopes or other different instruments. I hope now that you can also say you met the success criteria.